Section 3.7 Optimization Problems. Optimization is one of the most powerful applications of calculus to our everyday life problems, as we are always seeking to maximize the profit, minimize the cost, maximize the volume of a box, or minimize the distance, etc. Having said that, we will learn how to solve such problems in this section. Here is very helpful steps to solving optimization problems. Step 1. Identify all known quantities and the quantities to be found from the problem. Sketch if possible, because when we visualize, it makes a lot more sense and it's easier to set up an optimization equation. Step 2. Set up the optimization equation for the quantity to be optimized. Step 3. Make the optimization equation to an equation containing a single variable that needed to be optimized, using a substitution if necessary from the constraint equation, relating the variables from the optimization equation. Step 4. Determine the domain of the variable in the optimization equation that makes sense to the problem. Step 5. Find the maximum or minimum value using calculus. We learned from section 3.1 through 3.4. Step 6. Conform the answer using the second derivative test. I know it might sound like, what does this all mean? But as we go through the problem, I will remind you steps, so then it will all make sense what this steps is talking about. So let's actually look at the problem. Example 1. A manufacturer wants to design an open top box that has a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? So typically in optimization problem, the problem itself has every single information we need. So it's your job to find all the information that you need. So what was our first step? The first step is to identify all known quantities and the quantities to be found, and sketch if possible. So let's say you sketch that box, and let's now try to identify all known values and the quantities to be found. I see that this box is open top box. That's very important. That's because the surface area of this box is given. This is the known quantity. And if it's open top box, that means there's no lid. So therefore, we will not count the area of top square, since they said that this was a square base. That's also very important information, since the question is then asking you to find the dimensions of this box. So what do you mean by dimensions? Dimensions will be the length and width and height. That will be dimension of a box. So you have to find the length and width and height of this box that will produce maximum volume. So that's what you have to maximize. So your optimization task for this problem is to maximize the volume of this box. This will give us our optimization equation. And because the surface area of this box is given, that's gonna be your constraint equation. All right, so now let's go ahead and do then second step. What was the second step? Set up the optimization equation for the quantity to be optimized. So let's now try to set up an optimization equation. What are we trying to maximize? We're trying to maximize the volume of this box. Volume is equal to length times width times height. That's a volume of a box formula. But because they said that this was a square base, my length and width will be the same because it's a square. So you can call the length x, you can call the width x, and since they didn't say height is the same, height you can leave as a height h. So then this volume equation gonna be equal to x squared times h. All right, now I came up with the volume equation. So now let's go to step 3. Make the optimization equation to an equation containing a single variable. Oh, do you see how my volume equation has x and h? There are two variables, and we want this to be a function of one variable. So we want to get rid of one of the variable, either x or h, but probably h, because if you get rid of x, then we have to square it. So how do we get rid of it? You get rid of it from what's called the constraint equation. Constraint equation is an equation that will give me relationship between x and h. So where am I going to get that? You're going to get that from the fact that the surface area of this box is 108 square inches. So let's go ahead and come up with the constraint equation. We are given that surface area of this box is 108 square inches. Surface area of a box is a sum of areas of all faces. So 108 equal to, what will be area of this bottom? It's an open top, so you only have a one base. And that will be, since it's a square, x squared. Now, after that, because it's a square base, all the side should have the same area too. So this one, it is x times h, and this face is the same, x times h. Well, this is also height h, so this face is x times h. And on the back, right here, the back of the face is also x times h. So you have 4x times h faces. So this is my surface area constraint equation. So you can see this gives me relationship between x and h. So let's get rid of h here. So to do that, you want to solve for h and you want to substitute for h there. So my volume equation will have one variable only, namely x. So let's solve for h. So I have 108 minus x squared equal 4xh. So divide both sides by 4x. I found my h, and my h is 108 minus x squared over 4x. And now you're gonna substitute h for 108 minus x squared over 4x right there. So then my v, volume, become function of x, and my h is 108 minus x squared over 4x. So then one of the x in the denominator cancel with the one of the x on the numerator, and let's distribute the x, and let's pull out the 1/4 in the front. So my volume equation become 1/4 108x minus x to the third power. What do we do now? What is the next step? Step 4. Determine the domain of the variable in the optimization equation that makes sense to the problem. Okay, so what is the domain? Well, x is the length, so it cannot be negative, it cannot be 0, because x was 0, then I got no box. So x has to be greater than 0. And now, next step is to find the maximum or minimum using calculus. And what is that we have to do to find the maximum or minimum? We find the derivative. So v prime of x is, this is just 1/4 times derivative of 108x is 108 minus derivative of negative x to the third power is 3x squared. And this will be never undefined, right? So does not exist, never happens. And it could be equal to 0 if 108 minus 3x squared is 0, which means 108 equal 3x squared divided by 3 both sides. My x squared equal 36, which gives me x equal plus minus 6. But x cannot be negative 6 since my domain is x greater than 0. So you will choose critical number x equals 6. Okay, so I have only one critical number, so hopefully this will give me maximum volume. So how do you check it? You can check it using second derivative test. My critical number, I only got one, that's a 6. And then v prime of 6 is 0. And what is the v double prime? V double prime of x. You can take the derivative of v prime of x. So 1/4 is just 1/4. Derivative of 108 is 0. Derivative of negative 3x squared is negative 6x. And then what is the v double prime of 6? That is 1/4 times negative 6 times 6, which is negative number. That means what? At this critical number, I have a concave down, which will give me maximum here. So my v double prime is negative here. Conclusion is I do get maximum. So I found the x value, which is the length and width of the box. So it still gives me a task to find the h as well. How do you find it? Remember, we had a relationship between x and h right here. So you can find the h as well. And h is equal to 108 minus x squared. My x is 6, which produces maximum volume, over 4 times x equals 6, which is equal to 72 on the top, over 24, which is equal to 3 inches. So now you can answer the question. Question is, what dimensions will produce a box with a maximum volume? So your final answer is the dimensions to produce maximum volume is 6 inch by 6 inch by, height came out to be 3 inches. So dimension is typically, if you write 6 inch by 6 inch by 3 inch, it is understood that this is the length, this is the width, this is the height. Or you could give me a sentence saying that the dimensions that will produce a maximum volume would be length equals 6 inches, width equals 6 inches, height is 3 inches. Example 2. A manufacturer sells a product in closed cylindrical cans. Each can will contain 512 pi cubic inches of material. What dimensions will minimize the surface area of each can? So what is the first step again? First step was to identify all known quantities and the quantities to be found, and sketch if possible. Since they said cylindrical cans, let's say you draw a cylinder here, and let's try to identify known value. I see there is a known value of 512 pi cubic inches. And even looking at the units, since it's a cubic inches, you could totally tell it is the volume. And now, what dimensions will minimize the surface area of each can? So again, I have to find the dimensions of this can. However, this time I'm trying to minimize the surface area. So my optimization equation has to be surface area of a cylinder, and my constraint equation is the volume. So second step, set up the optimization equation for the quantity to be optimized. We would like to minimize the surface area. So now I need to write an equation of surface area of this cylinder. It's hard for me to remember all the formulas, so for the surface area of cylinder, I always remember the picture of how it's cut open. So let's say this is a can, then you can use the can opener to open the top, open the bottom, and then you can cut the side of this cylinder with scissor. Once it's cut open, this cylinder will look like a rectangle here because you cut the side and you open it up all the way, and there will be top lid and bottom lid of the can. And the radius of this circle will remain the same in radius of the circle. Height of this cylinder will stay same as height of this open cylinder. And only thing then I need to find out is the length of this, and that has to be equal to the circumference of this circle, and circumference of this circle is 2 pi r. So then now, without memorizing, I can actually find out surface area of this guy. So surface area is, what is the area of a circle? Area of a circle is pi r square, but you have two of them. So that will be 2 pi r square plus, I need to also count the area of this rectangle. This rectangle has length 2 pi r and width h. So area of that rectangle is 2 pi r times the h. So I found my optimization equation, and if you look inside, I have two variables again. I have a variable r and I have a variable h. So I need then step 3, make the optimization equation to an equation containing a single variable that needed to be optimized. So now find relationship between r and h, and then solve it for h equal and plug it in just h, then solving for r, since if you do, you have to square it afterwards and it might get more complicated. So let's find the constraint equation. And of course, constraint equation will be what's given to us, which is the volume of this cylinder. Volume is given, and they said it is 512 pi cubic inches. But then what's the volume formula? 512 pi equals volume of a cylinder is area of a base times height. And since your base is a circle, area of a base is pi r squared times h. That will give you the volume. So then we can solve for h, no problem. And to solve for h, we need to get rid of a pi r squared. So we are going to divide both sides by pi r squared, then pi's get canceled, and you found the h, and h is going to be equal to 512 over r squared. And of course, you are going to substitute for h in your optimization equation so that you could only have a single variable. So now you're going to plug into right here, of course, for h. So now we're going to get surface area. Let's use the single s, and you're only going to have one variable r now. So this can be function of r. That will be 2 pi r squared plus 2 pi r, and my h is 512 over r squared. So then surface area function is 2 pi r squared plus r's get canceled. So I only have a 1 r in the bottom. And 2 pi times 512 is 1024 pi. And instead of over r, let's make it to the r to the negative 1 power. So when we take the derivative, it's ready to go. So now that we have s of r function, 2 pi r squared plus 1024 pi r to the negative first power, it is time to do step 4 to determine the domain of the variable in the optimization equation that makes sense to the problem. So my variable in my optimization equation is variable r, and since r is the radius of the can, and radius of can cannot be negative, it cannot be 0, so domain of r is r greater than 0. So now do step 5, find the maximum or minimum using calculus. So now, again, let's take the derivative, find the critical number, and then we can test in the second derivative to see if it is giving us indeed minimum. So my s prime of r then is equal to, take the derivative of 2 pi r squared with respect to r, it is 4 pi r. Take the derivative of 1024 pi r to the negative fourth power. It is negative 1024 pi r to the negative second power. And since negative second power is rational expression, let's go ahead and send it to the denominator. So that's a 4 pi r minus 1024 pi over r squared. So let's get the common denominator again so that it's easier to find the critical numbers. So common denominator is r squared. So I'm going to multiply top and bottom of the first expression by r squared. So I get 4 pi r cubed minus 1024 pi. I'm going to factor out 4 pi on the numerator, and I get r cubed minus 256 over r squared. All right, so what is my critical number? I have now 2 ways to get the critical number, because this expression right here would be undefined if r is equal to 0. So this expression does not exist if r is equal to 0, but 0 is not in my domain, right? So even though this is a critical number, it doesn't fit in this word problem. So we're going to disregard that. And this expression s prime of r would be equal to 0 if the numerator is 0. And numerator is 0 if r cubed minus 256 is 0. So let's work on the side. I have r cubed equal to 256. Take cube root both sides. So then r is equal to, if you are to use calculator, 256 to the 1/3 power. And you get about 6.35. That's my critical number, and I only have one. So last step, we want to make sure that this critical number is giving me the minimum that I desire. So my critical number x is 6.35. S prime of 6.35 was 0. To find the second derivative, it's better to use this one, because it's in the power form, so it's ready to go. So s double prime of r is equal to derivative of 4 pi r with respect to r is just 4 pi, since it's a linear, and minus 1024 pi r to the negative 2. When you take the derivative of that, bring the negative 2 down, it becomes positive now, and twice of 1024 become 2048 pi r to the negative 3rd power now. So I'm not gonna put it together as a one expression because I'm not gonna try to get a critical number at all. I'm trying to find out what's the sign of S double prime of my critical number 6.35 is. So I'm just gonna write like that and now test the S double prime of 6.35. So 4 pi is already positive, and then 2048 over 6.35 to the third power. You don't even have to calculate. Everything is a positive number. So this is going to be positive, which means it's a concave up, and a critical number at 6.35, you have a minimum by second derivative test. But again, go back to the original problem. Problem was asking what dimensions will minimize the surface area of each can. And earlier, like we said, a can have a dimension only the radius and the height. We already do have a radius. We found the radius has to be 6.35. Now we have to find the height h. And where do you find it? Right here. Very good. We can find the h from right here. So let me erase a little bit to find the room here. So then let's find the h. So then h is equal to 512 over r square, and r is 6.35 square. Now use calculator. 512 divided by 6.35 quantity square is equal to, I got about 12.7. So now you can answer the question. Dimensions has to be r equal 6.35 inches and h is equal 12.7 inches. I used approximately equal to because I did get non-terminating decimal. So here is my answer. In next 3 examples, we're going to omit showing the steps, how to minimize or maximize, so that we can actually do it without looking at them. So let's try to do example 3. Which points on the graph of y equal 4 minus x squared are closest to the point 0, 1? So let's verify what's given to me. I'm given a function y equal 4 minus x squared with a point 0, 1. And I'm trying to find the point. So my answer has to be ordered pair point, x, y, such that distance from the x, y to 0, 1 is the closest. So what do you say, guys? If my distance has to be closest from 0, 1 to x, y, am I maximizing the distance or am I minimizing the distance? Yes, you will like to minimize the distance so that it is closest. So now, let's try to graph here y equal 4 minus x squared. That would give us a better idea what we're trying to do here. So y equal 4 minus x squared is a pretty simple graph. The vertex is 0, 4, and it's a parabola upside down since the leading coefficient is -1. So this is my x-axis. This is my y-axis. Then this is 1, 2, 3, 4. So here's my vertex. And because this y also factor 2 minus x, 2 plus x. So I can see my two zeros are -2 and a +2. So if I just sketch briefly, my graph looks like that. And where is my fixed point 0, 1? 0, 1 is right here, and it is fixed. So out of all the points that are on this graph, I don't know which one. I'm trying to look for a point x, y such that the distance between the 0, 1 to x, y is the smallest possible out of all the points on this graph. Get it? So let's set up then optimization equation. We can start by looking at the distance of 0, 1 and x, y, right? So distance formula, if you recall, between 2 points on the plane x1, y1 and x2, y2 was x2 minus x1 square plus y2 minus y1 square. So now one of our point is 0, 1. We can call that x1, y1. The random point x, y on this graph, you can call it x2, y2. So then my distance between them become x minus 0 square, which is just x square, plus y minus 1 square. But now, this is still function of two variable x and y. And I need a relationship between x and y so that I can get rid of one of the variable. So where is my constraint equation? Well, it has to be somewhere in the problem, right? So constraint equation is, yes, right here. Y and x has a relationship such that y has to be always equal to 4 minus x squared. So you're going to use this constraint equation, and since it's already solved for y, let's plug y for 4 minus x squared right there. Yeah? Then my d becomes x squared plus my y is, it's a 4 minus x squared. So 4 minus x squared minus 1 squared. Write one more time. I get x squared plus 4 subtract 1 become 3. So it becomes 3 minus x squared squared. So now I gotta find the domain of this function, and note that because it's a square root function, my input has to be positive, but every x is x squared. So no matter what x you plug it in, it's gonna turn into a non-negative. So therefore, domain for this guy will be all real numbers. Now, is this function what I'm going to use to minimize? Do I have to take the derivative of this guy? Not really. So when you have a function like this, think of one more step. Okay? In order for you to make this square root of what's inside to be the smallest, you just can make radicand smallest instead. Because the smaller the radicand, radical is smaller. So therefore, I'm going to create a new function called the f of x. And I'm gonna just set that equal to what's inside of a radical. And I'm just gonna minimize f of x. Because if fx is minimized, square root of smallest number will be the smallest. Make sense? So you know how to make a problem simpler in the future if you have a function involving radical. And if you are trying to minimize, then now you can just set radicand equal to another function and you can just minimize that instead. Okay? So now to find the critical number, I'm gonna find f prime of x. And f prime of x is 2x plus, this is a function raised to the second power, so you need to use a chain rule. Outer function, when you take the derivative of outer function, it is 2 times inner function to the first power, which we don't have to write the first power. And then you multiply by derivative of inner function, and derivative of inner function is negative 2x. This f prime of x has a common factor 2x and 2x. So I'm going to factor that out. If a 2x comes out, it's 1, but this whole thing is actually negative because of the last factor is negative. So it's going to be negative. And since 2x is out, what you have left is the 2 times the 3 minus x squared. So if you simplify that, you get 2x times negative 2 times negative x squared is a 2x squared. Negative 2 times 3 is negative 6. Negative 6 plus 1 is negative 5. And that's what my f prime is. Is my f prime ever undefined? No. So does not exist, never happens this case. And only way you're going to get a critical number is if my f prime is 0. My f prime of x will be 0 if x was 0. So that's one of the critical number. My f prime of x will be 0 if 2x squared minus 5 was 0, which would mean that 2x squared is equal to 5. And then you divide both sides by 2. So your x should be then x is equal to plus minus radical 5 over 2. So those are another 2 critical number of yours. So I have 3 critical numbers that I found. Now it is time to do the second derivative test on these critical numbers to see which one is giving me the minimum. So my critical numbers are negative radical 5 over 2 and positive radical 5 over 2. And I have 0 in between. And this d prime of x will be my f prime of x, and this will be my f double prime of x. But because it meant distance, it says d prime of x. Anyways, so you can call it f prime of x, you can call it h prime of x, you can call it g prime of x. That's not a problem here. So these are all 0. Remember, this is how we got the critical number for setting f prime equals 0. So their f prime is all 0. Now I have to find the f double prime of x, and I gotta test these 3 points to see if it's a concave up or concave down to determine which one gives me maximum or which one gives me minimum. Okay, so now let's see which one is the best f prime of x to take the derivative of. From what I have here, I like this one the best. And we can use a product rule to find the f double prime of x. So let's now find the f double prime of x. And because we're going to use product rule, so it's f prime times g plus f times g prime. That's my product rule. So derivative of 2x is 2. G, I just copy, plus f 2x. G prime is 4x. So then it is 4x squared minus 10 plus 8x squared, which is equal to 12x squared minus 10. So I found my second derivative. So let's test signs for each of my critical numbers. Notice that my f double prime is 12x squared minus 10. So whether I plug negative radical 5 over 2 or positive radical 5 over 2, I'm gonna get the same number as f double prime of those. So let me just test that for 2 of them at the same time. 5 over 2. You can only do that if it's gonna give you the same result. And that's a 12 times plus minus radical 5 over 2 squared minus 10. And that's equal to 12 times 5 over 2 minus 10. And 2 and 12 cancel, and that's a 6. 6 times 5 is 30. 30 minus 10 is 20, which is positive number. So f double prime of negative radical 5 over 2 is positive. F double prime of radical 5 over 2 is positive. And because it's a positive, that means it's a concave up. Remember, concave up is a cup. So at the critical number, you have what, guys? You have minimum. So I'm going to have a concave up here, which means minimum as well. What about f double prime of 0? At 0, I get 12 times 0 square minus 10. This is 0. I get negative 10. So my f double prime of 0 is negative, which means it's a concave down. And because it's a concave down, at 0, I'm gonna get a maximum. So you can see that now you're gonna have two pairs of points, which gives the minimum distance from 0, 1 to these points. But these are both x coordinate of the points. So now I need to get the y coordinate. And again, where do you get it? You get it from the constraint equation. Y equal 4 minus x squared. You got the x value, so now you plug it in right there to find the y coordinate. So let's use right here to get the y coordinate. And y is equal to 4 minus, my x is plus or minus radical 5 over 2. But again, when I square it, it's gonna both become positive. So let's use it at the same time. Then I get 4 minus 5 over 2. So that will be 8 minus 5 over 2. So it is 3/2. So my closest point are radical 5 over 2, comma, 3 over 2. There's one more, right? Negative radical 5 over 2, comma, 3 over 2. And here is my answer. Example 4. Suppose a rancher has 200 feet of fencing with which to enclose two identical rectangular corrals that will share one common side. What dimensions should be used so that the enclosed area will be a maximum? Okay, so let's see what's given to us. We're given we have a 200 feet of fencing material. So if it's a fencing material, what would that be? That is perimeter. So what's given to me is perimeter P. And the question is, what dimensions should be used so that the enclosed area will be maximum? We're trying to maximize this area. So we want area to be maximum. So our optimization equation will be, of course, area of this rectangle. And question is, what dimensions? So I'm going to call the length of this rectangle x, and I'm gonna call width of this rectangle y. So my answer has to be x is what and y is what. Okay, so now let's set up an optimization equation according to my variable length equal x, y equal width. What would it be area function, since that's what I have to maximize? As you know, area of a rectangle is length times width. So that will be x times y. And because my area function has two variables, x and y, I have to get rid of one of them. So now I have to find the constraint equation. And where am I gonna get constraint equation again? Yes, I have to get it from the fact that perimeter of this fencing is 200 feet. Now, you actually have corrals that share one common side. So you actually have three y's, right? This is also length y, this is also length y, and you needed to put that y in the middle. And then I do have another x on the top. So the whole perimeter of this corrals will be 2x plus 3y, and that has to be equal to 200 feet. And let's get rid of y. Then I will have 3y equal to 200 minus 2x. Divide both sides by 3. I get y equal 200 minus 2x over 3. So now, of course, you're going to plug this into right here. Your area become function of x, as you're going to only have one variable x. and it's x times y, and my y is 200 minus 2x over 3. So then I'm going to distribute this, and I'm thinking about taking derivative soon. So, I'm just gonna make this look like a polynomial. It's very easy to take the derivative then. I don't want the product, I don't want the quotient. So let me just rewrite this as a 200 over 3x. X is distributed. Next term is negative 2/3 x squared. And what is the domain? X is the length of this scroll, so it cannot be negative, and it has to be a positive number. So domain is x has to be a positive number. Now we're going to take the derivative, a prime of x, and derivative of 200 over 3x is 200 over 3. Derivative of negative 2/3 x squared is negative 4/3 x. And this is never undefined. So does not exist, never happen. And only way I'm gonna get a critical number is if a prime of x was 0. And set that equal to 0. I get 200 over 3 is 4/3 x. You can multiply by reciprocal of 4/3, which is 3/4 both sides. So then x has to be 50. If x is equal 50, my a prime is 0. So now I can do the second derivative test. What's my critical number? It is 50. And what's a prime of 50? It is 0. What's a double prime? Let's calculate a double prime now. And you can get it from right here, of course. And derivative of 200 over 3 is 0. Derivative of negative 4/3 x is just negative 4/3. Oh, I just got a constant. What does that mean? No matter what the input is, your a double prime is always negative 4/3, meaning it is concave down the whole time for all x. So then a double prime of 50 is also negative 4/3, since my a double prime is constant. No matter what you plug it in, it just stays negative 4/3. So it is negative, and because it's negative, it's a concave down. And if it's concave down, what are you getting? You're getting maximum. When x equals 50, you get the maximum area. But again, go back to original question. I am also supposed to get the width as well. I only found the length. So where am I gonna find my y? Right here. You notice you always get your second variable from your constraint equation. So now you can find your y, and your y will be equal to 200 minus 2 times my x has to be 50. And if x has to be 50, then that's a 200 minus 100, which is a 100 over 3. And that's your y value. That is the width that produced the maximum area. So my final solution is dimensions, length equal 50 feet, and my width is 100 over 3 feet. So this is my answer. Last one. Example 5. Find two positive numbers such that the second number is 2 more than the reciprocal of the first number, and their sum is a minimum. So I have to find two positive numbers. So let's call them x and y. So I need to find x and y, but they said it has to be a positive number. So as I set up my variable, I got my domain as well. And now, what kind of two numbers? I want two numbers such that the second number is, which one do you want to call second? Y? Okay. So second number is means equal to, more than is plus the reciprocal of the first. So first one is an x. So reciprocal of an x is 1 over x. And that's not what I am trying to maximize, right? You want the sum to be the maximum. So your sum is the optimization equation, which is the sum of these two numbers, x plus y. But this is the condition, which is your constraint equation. Y has to be equal to 2 plus 1 over x. So now I want my optimization equation to have only one variable. So we're gonna, of course, replace y by 2 plus 1 over x. So then my sum function becomes function of one variable x, and it will be equal to x plus y is 2 plus 1 over x. So my sum function, one more time, I'm gonna rewrite as a power so that it's easy to take the derivative of. And my domain is x has to be a positive number, and it's written above already. So I'm ready to take the derivative of this guy, and s prime of x is 1 minus x to the negative second power, which is equal to 1 minus 1 over x squared, which is equal to x squared minus 1 over x squared then, and x squared minus 1 factors, x plus 1 times x minus 1 over x squared, and you can see this will be undefined if x was 0. But now go back to your domain. We're looking for positive number x, and if x is 0, it's not positive. So we're going to disregard that. And my s prime will be 0 if numerator is 0. And my numerator is 0 if x was plus minus 1. But again, remember my domain is x has to be a positive number only. So only critical number that I can take is x equal 1. This is my only critical number. So let's go ahead and do the second derivative test. My critical number is 1. S prime of 1 is 0. Now find the s double prime. I'm actually going to use this one to take the s double prime of x because it's easier to find the derivative. My s double prime of x equal derivative of 1 is 0. Derivative of negative x to the negative second power is negative second power comes down, and it becomes positive 2x to the negative third power, which is 2 over x cubed. So s double prime of 1 is 2 over 1 cubed, which is 2, which is a positive number. And positive means it's a concave up. Concave up looks like a cup. Then at critical number, you're going to have minimum. And we want the sum to be the minimum, right? So s plus y will be minimum if x was 1. So now, remember, we have to find two positive numbers, x and y. Your first number you found is an x. So now I have to find the second number. And yes, you get to find the second number from your constraint equation. So your second number, y equal 2 plus 1 over x, and x has to be 1. So then that's a 2 plus 1, which is 3. That means the y has to be 3. So your answer, two positive numbers, are 1 and 3. All right, guys, I hope this gives you really good idea of how to maximize or minimize. And now you know how to solve any optimization problem using calculus.